Hello and welcome to our video presentation. We are Group 8 and we will be introducing our modular aiming and triggering device. For this project, we had to create a modular system which helped people with high-level disabilities with the aiming and triggering of external devices. Initially, we thought of creating a fully robotic arm which would be controlled via a joystick, eye gaze, or voice input. However, we reached out to some patients from the M.A.T.S clinic at Royal London Hospital. M.A.T.S stands for motor neuron disease, and it is a neurodegenerative disease that causes muscle weakness by affecting the motor neurons that control muscles. We decided to make this the target population for our product. From our meeting with them, we realized that instead of a robotic arm, they wished to recover their ability to use their arms and hands independently and be in direct contact with everyday objects. We then redefined our objectives and opted for a device that would help with the aiming and triggering of the actual arm and hand of users. Our final product is therefore a modular device consisting of two separate systems that come together to allow full motion of the arm as well as gripping ability of the hand. Firstly, we have a dynamic arm support, which is a fully mechanical passive system. It involves a counter-gravity mechanism using elastic bands, while also allowing complete freedom of movement of the arm. It attaches to the forearm using a Velcro strap, and the dynamic arm itself is attached to a wheelchair via an adjustable wheelchair attachment. Acrylic was chosen as the material given its low density compared to metals, good rigidity, ability to sustain small amounts of bending, and ease of manufacture. The wheelchair attachment prototype secures a dynamic arm to the wheelchair, allowing for different shoulder lengths. The second system is a voice-activated, Raspberry Pi controlled, pneumatic actuator hand device. Silicon-based actuators consisting of stretchy network of chambers and a rigid base enable an inward bending motion when air is pumped through them, allowing the user to grip and firmly hold objects up to 1 kilogram. The actuators are sturdily mounted on the user's hand by means of a special strap. The airflow is enabled through pumps and regulated by a series of electrical and mechanical valves. The mechanical valves prevent the backflow of air, while the electrical valves allow air exhaustion to bring the actuator back to its original shape.
Close.
Using a speech-to-text API upon recognition of keywords from the user, the corresponding signals activate circuit components, enabling the actuators and the glove function.
Meeting user requirements is a central concern in any engineering application, especially if the proposed device is intended to be wearable. Despite the difficulty in identifying the typical M&D patient, being symptoms, stages, progression, and age so different, we think our device meets the user needs in several ways. The first one is modularity. Both the hand triggering device and the mechanical arm support can be used independently from each other, which represents a huge advantage in terms of addressing different degrees of severity in the disease progression. The second one is adjustability. Soft straps on the arm support device adapt easily to various arm sizes, and the wheelchair attachment allows for different shoulder heights. Similarly, thanks to the Velcro base, actuators can be moved around on the hand strap to best fit different finger lengths, and the hand strap itself can be tightened or loosened to fit various hand and wrist sizes. The third one is versatility. The structure of the arm support doesn't restrict the user to a few fixed movements, allowing rotational freedom of shoulder and elbow, and the hand gripping device makes the most of the patient's hand ergonomics, allowing manipulation of a wide range of everyday objects. Finally, user-friendliness and cost. The product is easy to mount and use, is not bulky and unaesthetic, and is designed around the user, with the key idea of amplifying all strength and motor control left, rather than merely substituting them.
For future improvements, our first consideration aims to reach more users and make the device more adaptable. For the passive arm support, we can design the device to be more adjustable for users with varying arm lengths, possibly using sliding or flexible parts. A harness-mounted alternative for users not wheelchair-bound should be designed, opening the device to all stages of M&D as necessary, effectively also increasing the modularity. For the glove actuator, we can adapt the input interface as latter stage loss of verbal function will impact the usability of the device. Separate input interfaces can be designed as interchangeable modules for different needs, such as using pressure sensors, eye gaze technology, or electrodes. Secondly, we can improve the manufacture and usability of the device for a better user experience. For user safety, an accessible see-through sheath can house elastic bands on the arm support to eliminate any risk of harm from snapping due to high tension. 3D printing the actuator and using a PCB could drastically improve the ease and effectiveness of the manufacturing and make the device more reliable and sleeker. The speech-to-text service currently requires a Wi-Fi connection and a paid subscription. Both problems could be solved by using locally hosted, self-trained Mozilla Deep Speech, increasing accuracy and security. A compiled language, instead of Python, could improve the actuation time. The aforementioned changes would be necessary improvements for mass production. We would like to acknowledge the following individuals or entities for their help. Thank you for watching, from all of us.